Greetings. Welcome to DAU's AI Video Learning Series. This video is going to provide you insights into the fundamentals of a simple neural network. I'm going to provide you an overview of the construction, the training of a simple machine learning model. So this is a graphical representation of a biological neural network. Now for our purposes, we're just going to greatly simplify a bit of neuroscience here and talk about the neurons, which are these items here. They're connected through axons, and where they actually come together is a synapse connection. And you've probably heard the old saying, neurons that wire together fire together. Well, the size of that synapse connection grows the more those neurons fire, and that's how the network learns. So this is the representation of a simplified artificial neural network as opposed to the biological one. Now the circles represent the neurons, and we sometimes call them neurons or nodes, just nodes. And the leftmost layer of neurons you see there, the leftmost circles are called the input layer. The layer to the far right is the output layer, and then those two layers in the middle, those are called hidden layers. And the lines connecting those neurons to the other neurons, those represent the synapses in the biological network. Inputs come in from the input layer, then they pass through those connections to that first hidden layer, and then they continue to propagate from left to right to the second hidden layer and then on to the output layer. Now for completeness, I ought to mention that inside each of those neurons is a little activation function, which adds a degree of nonlinearity to the network. Now don't get too hung up on that, it's just a piece of math. So the inputs come into a various neuron, they get summed together to run through that activation function, and that's what determines the magnitude of that output. Okay, so the thickness of each of those synapses in the biological network represents the how often they fire. We kind of model that with a parameter or a weight that's associated with each of these connections. Now that numerical value of that synapse connection, if you will, that we could kind of think of that as represented by a knob. So when we train the network, when the network learns, that knob gets turned up and or turned down in a similar manner. And during the training phase of that network, we adjust all those knobs. Now there are two phases usually to the life of a network like this. There's the training phase where you adjust basically the algorithm adjusts all the knobs, and then there's the usage phase where once it learns, then you leave all the weights alone, you leave all the knobs set, and then you take it out and use it. And the way you train it is inputs will come in. You'll have to have a good data set. And for every set of inputs, so you'll put an input in here, it'll propagate through the network and produce an output. Now, before it's trained, that output is rarely what you want it to be. So you compare it to a piece of truth data that's associated with the inputs, and you get an error function. And then the backpropagation algorithm uses that error function to backpropagate through here and adjust all these weights, then backpropagate again, adjust all the weights associated with all these connections, backpropagate again, adjust all the weights associated with those connections. And you can kind of see the graphical representations of the little knobs here. So each one of these little knobs for every single pass would be turned a little bit differently, if you will. Back in the 90s, when I first started getting associated with neural networks, I had to do a project for my master's work, and I created a little self-driving car, if you will. But I had to simulate the car, I had to simulate the environment, so it was all a computer simulation, and I had to write all that. But then once I got all that done, I had to come up with how the car was going to sense the environment, and I came up with this little linear sensor on the front where these little 8 linear sensors would just look out at the road in front of it and take a snapshot of it. And that would determine whether the car would steer to the right or steer to the left or stay straight. And all I did was steering. I didn't worry about the speed. So if I plug that into the network, here's the input from those little sensors. And if you put a car there, you can kind of get a better idea maybe. So on the leftmost side, I had a little sensor that looked out. And on the rightmost side, I had a little sensor that was looked out. And they were linearly spaced in between there so that we got a little snapshot of the road in front of them. And then that was fed into the network. And a steering output would come out that would say, turn left, hard left, depending on this numerical value that came out of these 4 inputs, would be, hard left, stay straight, turn right, whatever. Okay, so now I had the environment set up, I had the sensor created, now I had to come up with a data set. And when you work with much of this AI, you realize this data set's really where most of your work is, and this is where the most important stuff is that you do. And for every data point I created, I would take the car out, I would put it on the road, and I would take a snapshot with a sensor of what the road looked like in front of it. So I put it in every various orientation and everything every situation I thought the car might get itself into as it drove around, and I'd take a snapshot. And then I had to create a piece of truth data to go along with every one of those snapshots. So in this case, the truth data might be, hey, I want to turn hard right, or I'm going to run off the road. And then take another snapshot, and this one might be, hey, a slight left to get back into the middle of the road. This might be a little more of a left turn to get back on track. And then this one might be a stay straight, because I got, if you can see the sensors, I got road over here, I got road over, or I got edge of the road over here, I got edge of the road over here, and I got clear road right in the middle. So that one might be a stay straight. So remember this one, and we'll take this one and we'll train the network with it. Now we'll assume we've got all our data, and we're going to go into the training phase. So I got road edge over here, I got road edge down here, but I got clear road in the middle. Now I randomize all my weights in the beginning, because I need them set, I can't have them all set to the same value. So I randomize all my weights, I put the input in, the output's whatever the output is. We wouldn't expect it to be right because it's we haven't trained it yet. And sure enough, it's, let's say, a hard left. Okay, we compare that to the truth data, or the algorithm compares it to the truth data, which says continue straight. That's not right. So they calculate an error value between what actually came out and the desired output, use that error value to back propagate through the network, hence the name, and adjust all these weights, back propagate through the network again, adjust all these weights, back propagate another layer and adjust all those weights. That's a single sample of data. Okay, it has to do that for the entire data set, which is called an epoch, and usually multiple epochs. You run it through the complete data set multiple times until you start seeing your error rate get down close to zero or to an acceptable value. Once that happens, you can deem the network trained. And again, it usually takes multiple epochs for that to happen. But once it is trained, I took it out on my track and I would run it through my track, and it usually did pretty daggone good. It would usually stay right in the middle of the network and run down the middle of the track. I had different tracks. I had circular tracks. I had figure eight track, whatever, and it would usually do great. It would stay right in the middle of the road. When I got into trouble is when I would put it on a track that didn't look like the track I'd trained it on. So for here, I've got an elevated track. I've got yellow stripes down the road where I didn't have that in my training data. And if I did a situation like that, I'd usually get into trouble and see something that I really didn't desire. Okay, so that was a simple, easy to understand example, but that's pretty much how neural networks today still work at their core. Of course, today, there are generally many, many more neurons, many more connections, and almost certainly more sophisticated training algorithms. But at their basics, the mechanics are the same. And sometimes you lose insight into what's actually going on with adjusting the layer weights, and that's how you're training the network. So back when I did this, I did it in C++. And it took well over 100 lines of code just for the neural network part. The environment was many, many more lines than that. But today's modern tools and modern languages make it so much more straightforward, or more efficient anyway. This is a little piece of Python code that sets up this network, and you can see it's pretty much just calls. Set up a dense layer and train on your data set, and there you go. Not as hard as you might think. You can take Python courses if you'd like. Through DAU, you can do a learning search on assets, and I think we have over 100 different Python courses in there that you could take if you'd like. If you'd like to take any of our courses from DAU and earn credit toward an AI training credential, then just go ahead and click here. And thank you very much for watching. And if you got something out of that, please leave a like and subscribe. Thank you very much.